Okay, so here is the most complicated linear algebra thing we'll see. Okay, so again, maybe you're not fluent in linear algebra. Maybe those computations that I did are not, super natural to you, but they're still easy. Okay, it's just a matter of practice. If you don't multiply matrices and vectors for a living like I do, maybe it's not natural to do, but it's not complicated. It's just taking products. Okay, and so the thing that we'll use that's probably a little more fundamental is this idea that if you start with a matrix which is symmetric and positive semi-definite, okay, we know what positive semi-definite means, and for us it's certainly positive semi-definite because positive semi-definite means that if I look at U transpose sigma U, I actually get something which is non-negative. But we just proved that what we're getting is actually a variance, so that certainly has to be non-negative. So whether I have whether I have sigma, for which it's positive semi-definite, or I have S, for which I have a sample variance, which is also always non-negative, then I always have a positive semi-definite matrix. Okay? So this is the name that we give to those matrices. So let's use only the fact that they're symmetric for now. If I give you a symmetric real-valued matrix, A, saying D by D, then we know that A can be decomposed in many ways. You can look at any book on, say, numerical linear algebra, and you will find a million decompositions like, Koleski, QR, whatever you want. The one we're interested in here is the spectral decomposition. And this spectral decomposition, let me check which notation I picked for that one. Yes, is A can be written of the form P times D times P orthogonal, where P is a D by D orthogonal matrix, and D is a diagonal matrix. Okay? Anybody remembers what it means to be an orthogonal matrix? Yeah, so P times P transpose is equal to P transpose times P, and it's equal to the identity. Okay? So what does it mean? When you look at P transpose times P, what you really are looking at is the inner products between the columns of P. Okay? And so that means that if you get 1 on the diagonal, it means that the length is 1. The squared norm is equal to 1. And if you get 0 on the off diagonals, it means that if you take one of those vectors and take the inner product with another vector, you get 0. It means that you have orthogonal vectors. So a matrix, an orthogonal matrix D by D is just a matrix whose columns are just orthogonal vectors and whose rows are also orthogonal vectors. Okay. So so we have this matrix P. It will matter, but let's focus more on the diagonal matrix. Okay, so if I were to look at this, I would have a matrix P transpose, or P, which would have entries everywhere, right? I mean, that's the typical case. Then I would have a diagonal matrix, which has entries only on the diagonal. Okay, and everything else is 0, and then you would have P transpose. Okay? So clearly, you have this diagonal matrix. It's going to have values on the diagonal, and those values do matter a lot. Okay, and so the diagonal elements of D are called the eigenvalues of A. And the columns of P are called the corresponding eigenvectors of A. So who has never seen eigenvalues, eigenvectors? All right, let's speed up. So I have this spectral decomposition. It's actually giving me something which is called eigenvalues, eigenvectors. You might have not seen it necessarily in the form of a matrix like this. Sometimes you actually write it as A is the sum of the diagonal elements times the columns of P transpose. There's many ways of writing it. If A is positive semi-definite or semi-definite positive, what do I know about the eigenvalues? That's usually the way we check it. Yeah? Yeah, they're non-negative. Okay? So if I know that I look at the spectral decomposition of sigma and or S, when I'm going to write this, let's say I just stuff it into MATLAB and I say compute the eigen decomposition, the diagonal matrix I'm going to get only has non-negative entries on the diagonal. It turns out that those non-negative entries are also variances. And they're variances when I project not on any direction u, they're variances that I get when I project on the eigenvectors themselves. Okay? So an eigenvector, a matrix of eigenvectors is just a change of basis. Just like here, I would say, okay, I have this basis, my xy axis. I could change to that basis, which would be my basis of eigenvectors. And the eigenvalues are just telling me how much variance I have along the new axis that I set out for me to take.